We're addressing the electrical reconfiguration of an old hospital campus being renovated into low-income housing. 4 buildings are being converted into housing units, each with 19 to 27 apartment units, each with its own metered board and all electric appliances. 2 methods for reconfiguring the electrical distribution are being considered. Method 1 involves individual transformers for each building. This approach offers improved reliability because a single transformer failure will not affect multiple buildings. Maintenance becomes easier as transformers can be serviced or replaced without disrupting power to the other buildings. This method also provides flexibility. Buildings can be added or removed without impacting the entire electrical system. However, there are also potential drawbacks. This method leads to higher initial costs because it requires multiple transformers and additional wiring. Space constraints may arise as transformers require significant space in each building. Additionally, there is the potential for voltage imbalances if the transformers are not properly sized or balanced. Voltage fluctuations can occur. Method 2 involves a single transformer with a central meter module. This option offers a lower initial cost as only one transformer is required. It's also space efficient. The transformer and meter modules are located in a single building. Wiring is simplified, and feeders to the apartments can be routed through the existing utility tunnel. However, this method also has downsides. It offers reduced reliability. A single transformer failure will affect all buildings. Maintenance challenges arise. Any maintenance or replacement of the transformer will require coordination with all buildings. Voltage drop is a concern because the long feeder runs approximately 300 feet from the central meter module to the furthest apartments, may cause significant voltage drop. Considering the factors provided, the use of individual transformers for each building is the more reliable and flexible option. While this method may require a higher initial investment, it reduces the risk of a single point of failure and allows for easier maintenance and future scalability. The size of the transformer should be carefully calculated to handle the anticipated electrical demand from each building's 19 to 27 units, each equipped with metered boards and all electric appliances. Appropriate surge protection should be installed to protect the transformers from power surges. The utility tunnel should be inspected for adequate ventilation and accessibility for maintenance, and the feeder cable should be properly sized and installed to minimize voltage drop. Each building's electrical loads, including lighting, appliances, and heating or cooling systems, need to be accurately calculated to determine the appropriate transformer size and feeder cable capacity. Voltage drop calculations, using the feeder lengths and anticipated loads, are essential to ensure that the voltage at the furthest apartment units remains within acceptable limits, typically within 3% for power and 5% for lighting, as commonly recommended by industry standards and electrical codes. The existing utility tunnel needs a thorough inspection to verify its structural integrity, available space for the feeder cables, and environmental conditions such as temperature and humidity, which can affect cable performance.